This is number 11, and I want to consider the following equilibrium, and I'm taking, it looks like, benzoic acid, which I'm denoting with that. This is just another standard weak acid equilibrium, so what's coming next year? This is a weak acid. What's going to be next in the equilibrium?
Would it put water?
Yeah.
I was trying to say, but I had some in my mouth.
Yeah. And what's going to be on this side? So it's a weak acid. So I'm going to donate a
You'll have, you're going to have hydronium.
hydronium ion plus the deprotonated form, the conjugate base of benzoic acid, which is going to be C5H5COO minus aqueous. Using this notation, there's a lot of different equivalent ways I could represent it, so I'm doing that. And I wanted to fill in the bubble corresponding to the correct statements. This is, I think, one of the only multiple choice questions. And statement A, addition of benzoate, which is this, to the solution will lower the pH. Okay, let's think about that. What effect am I talking about if I talk about adding some benzoate to this equilibrium mixture?
You're going to push it more to the right.
But it is, what effect are we talking about? It's the,
You're adding more benzoic acid?
no, benzoate, the conjugate base. I'm going to add some of the conjugate base.
So it's going to pull hydrogens off the hydronium?
Well, it's going to, but what is it? The benzoate,
It's a conjugate base.
it's the conjugate base, and this would be what? The, what?
The proton receiver?
Yeah, but it's
The
going to be
oxidizer?
the common ion effect, because this is just an equilibrium, okay? And we're back to that French guy, what's his name? Yeah, the French dude, Le Chatelier. Le Chatelier's principle. So I'm adding some of this. At what point, so if I add some benzoate to it, is Q now greater than or less than K? What is Q again?
It's going to be a product of a reactant, so the product's going to be greater.
So if Q is greater than K.
Greater than K.
It could be.
If Q is greater than K, which way does the equilibrium go? It goes to the left, which is going to, in other words, this is going to go back to make, it's going to reduce this until it restores it to its equilibrium value. So if I'm lowering the amount of hydronium ions present, is that going to raise the pH or lower the pH? What happens as the hydronium ion increases?
Well, it's going to put more basic, less acidic.
Yeah, it's going to be less acidic
So
and
it's
going to raise the pH. So the question A says we'll lower the pH. So that's not true. B, option B, addition of benzoate to the solution will raise the pH. So option B would be correct. So B would be true. Addition. Gesundheit. So this is sort of a composite question. This is true. So option B is going to be one of the true options, and this is a composite because it takes into account Le Chatelier's principle, the common ion effect, and our understanding of pH. So it's a sort of a composite question. Now option C,
It's true.
addition of benzoate to the solution will lower the pOH, which is equally true, so it's equivalent. So C is true. Does I say lower or raise?
The next
It lowers
one's
the
raise.
pOH.
Lower, yeah. Because of the relationship between the pH, which we know will be raised, and the pOH. When the pH raises, the pOH goes down. So now option D, addition to the of benzoate to the mixture to the solution will raise, and I misspelled it, says razor the pOH, which we know is false. Although I liked razor better, yes, to give it a nice close shave. Okay, now, addition of hydrochloric acid to the solution will raise the pH. Now let's look at this. What would hydrochloric acid, because it's a strong acid, it completely dissociates, and it's going to do what in the what common ion is it going to kick in?
Wait, what?
It's going to add hydrogen.
It's going to add the hydronium ions, because hydrochloric acid being a strong acid is associated completely to chloride ions and hydronium ions.
Just to get more acidic.
So it's going to raise the concentration of the hydronium ions, okay, which is going to make Q greater than K. The process will respond, the equilibrium will respond in such a way as to lower it back. In other words, the reverse process is going to be favored again. And that is, this one is probably the most ambiguous of all of them. So is that going to have a net effect of, well, initially I add the hydronium ion, it's going to lower the pH.
It's kind of like the opposite of what we did in the beginning.
But it's gonna respond in such a way as to raise the pH back up. But I don't know if it would go above where it was, if it's going to raise it back above that level, because it's going to have to consume some of the benzoate in that process. It's going to have to reprotonate some benzoate to make it back to this. So that one's probably a bit on the ambiguous side, but I wouldn't expect it to really raise the pH in the fashion that adding the benzoate did, although it should. Yeah, I guess it almost,
It will raise.
yeah, it's going to raise the pH. The equilibrium's response to it's going to raise the pH. It's going to initially lower the pH, but then the equilibrium's going to push it back to this side, which will raise it back up again. See, we're in a buffer solution, so it's going to
be very slow.
it's going to raise it, but it's not going to raise it back above where it was. See my point? It's a buffer solution. It's going to resist changes to pH. So it's going to slightly, where it would normally lower it dramatically, because of the common ion effect and Le Chatelier's principle, it's a buffer now. We've got a solution of an acid and its conjugate base. So addition of some more acid to it is going to, because of Le Chatelier's principle, is going to respond to minimize the amount. It's actually going to have the effect of slightly lowering the pH, ever so slightly. So that means that it's not going to raise the pH. Whereas addition to this did. That will not actually raise it. Okay? So what is going to happen is it's going to slightly lower it. So that brings us to option F. Addition of hydrochloric acid to the solution. We're now talking about a buffered solution. It's going to very slightly lower the pH. Is everybody with me on that?
Yeah.
Okay. So if I slightly lower the pH, what happens to the pOH?
It goes up.
Goes up.
Yeah. So F is going to be true. Addition what was it? Addition of HCl. pOH. And I think I had that one wrong. I think I put that one wrong on the key, so I want to make sure to point that out in lecture. But this is a subtlety. These last two were in the buffering region. And so, yes, indeed, I add acid to it. It is going to it's going to lower the pH, but not very much because we've got a buffer.
Well, when I did this problem, I thought about it like in the beginning when we added the base to it. It raised the pH because even though the reverse reaction was favored,
Yeah.
we were still adding base to it.
Yeah.
So I figured we added acid to it, so then the reverse was favored, but
Yeah.
we were still adding acid.
Yeah. Well,
So I thought the opposite, since it is the opposite. And,
but
you're
it's,
saying they're the same thing?
we're in the buffering region. Adding an acid to, adding hydrochloric acid to any solution is going to lower the pH. But if I added, the example on buffering, or if I add 1 ml of acetic acid or hydrochloric acid to 9 mL of water, I'm going to see a dramatic drop in the pH. It's go down to like 5 pH units. If I add 1 ml to 9 mL of a buffer solution, it only lowers the pH a tiny fraction, like 1/100th of a pH unit, because of the buffering action. That's because of the equilibrium Cohen-Ion effect. So indeed, it does still lower it, but ever so slightly. Okay. So it resists dramatic changes.
Yeah.
Okay. That's what. This is a subtle question, but so I'll take a little bit of time. I want to talk about this in the lecture room.
Okay, good.
Okay. So is that good on that one? Okay, good. That's a wrap.